A few months back, I sat with an engineer drilling for this exam, and I watched him lose a question he actually knew the answer to. He read the first line of the scenario, recognized the setup, and picked the option that would obviously work. But the clause that decided the question was sitting 3 sentences down, easy to skim past. It said the action had to be reproducible for an auditor, and that one clause ruled out the answer he chose. He knew the material cold. He just didn't read to the end. That's how people fail this exam, not on knowledge, but on reading. So here is the question worth holding on to the whole way through. When several answers all look right, how do you tell which one the exam is actually asking for? The items are built so that most of the options look correct until you find the one clause that separates them. So this episode isn't more theory, it's the reading method run against real questions until the method is automatic. That's the one question I want you holding onto the whole way through. When several answers all look right, how does an architect tell which one the exam is asking for? We'll dissect the 3 sample questions the official guide publishes, and then 9 more I wrote in the same style to cover the ground the samples skip. To be straight about that, the 3 are the guide's own public examples, and the 9 are mine, built to match the blueprint, not copied from any real exam. Before the questions, here is the method, and it's only 3 moves. First, read for the constraint, not the topic. The stem describes a system, and buried somewhere in it is the clause that actually decides the answer: a must, a never, a limit, a regulator, a cost ceiling. Find that clause and underline it in your head before you even look at the options. Second, eliminate by principle. Don't ask which option sounds smart. Ask which principle the question is testing, name it, and throw out every option that breaks it. Most items give you 4 options, A through D, and eliminating by principle usually clears most of them on the first read. Third, when the item lets you pick more than one answer, judge each option on its own. The exam mixes single answer and multiple response items, and every item tells you exactly how many to choose, so you treat each option as a separate true or false against the stem. Sample 1 from the guide, and it lives in the integration domain. A team exposes a customer support agent that can read tickets, draft replies, issue refunds, and delete user accounts. The support staff only ever need to read tickets and draft replies. The worry is that the agent could be talked into using a tool it should never touch, and you are asked which change best reduces the risk. Option A adds logging to the refund and delete tools so misuse can be audited later. Option B removes the refund and delete tools from the agent's configuration entirely. Option C keeps all the tools but adds a confirmation prompt before refunds and deletions. Option D replaces the agent with a larger model that follows instructions more reliably. Read for the constraint. The agent's job is reading tickets and drafting replies, so refunds and deletions are power it was never meant to have. The principle is least privilege. A system gets exactly the permissions its job requires and nothing more. So you strip out the tools it never needed, and the guide's key agrees. The answer is B. Logging is compliance theater. It records the deleted account after it's already gone. The confirmation step just gold plates a control onto power you should have deleted. And the model size has nothing to do with what the agent is allowed to do. Keep that move in your pocket, because you are about to see it again. Sample 2, still from the guide, this one in the models and context domain. An application sends the same large static system prompt and policy document on every request, followed by a short user message that changes each time. Latency and cost are both a concern, and the question asks which optimization most directly addresses both. Option A truncates the policy document down to its opening tokens. Option B switches to the smallest available model regardless of task fit. Option C places the static system prompt and policy before the dynamic content and turns on prompt caching. Option D moves the policy document into a few short example block. The constraint is the word static. The same tokens ride along every request and almost none of them ever change. Anthropic supports prompt caching, where you put the static content first as a fixed prefix and the model reuses it instead of reprocessing it. And a cached read costs just a small fraction of a fresh one. So you order the stable content first and cache it. Latency and cost both drop, and the guides key says the answer is C. Truncating the policy throws away context the system actually needs. Switching blindly to the smallest model risks quality to save money, and moving the policy into a few short blocks never creates a cacheable, reusable prefix. Sample 3, the last of the guide's own from the evaluation and optimization domain. A retrieval system suddenly starts giving confident but wrong answers right after the documents were refreshed, while latency and the model version never changed. The question asks for the most likely first place to investigate. Option A says the model weights have silently changed. Option B says the retrieval and indexing step is returning irrelevant or stale chunks. Option C says the temperature setting is too low. Option D says the context window has shrunk. Read for the constraint. Nothing changed except the documents, so the fault has to be where the documents entered the system. That's retrieval. The index is stale or mismatched after the refresh, so the system is confidently feeding the model the wrong chunks. The guide's key says the answer is B, the retrieval and indexing step. None of the other options would be triggered by a document refresh, so they don't fit the one thing that actually changed. Now, here is the thing worth stopping on. 3 samples, 3 different domains, and the correct answer rhymes every single time. Not one of them was a bigger model, and not one of them was more machinery bolted on top. Everyone was the same architect instinct: find the real layer, take away what shouldn't be there, and settle on the simplest design that meets the constraint. That instinct is what the whole exam is quietly testing. So once you see the pattern, most of the options disqualify themselves before you finish reading them. Now 9 of our own, same style, and again these are mine, not real exam items. Let's start with solution design. A team ships a ticket classification system with a clean shape, input, model, and an answer to the user, and at launch it works well. Over months it slowly drifts. New ticket types appear, accuracy slides, and nothing ever improves because corrections never flow back anywhere. Option A is to switch to a larger model so it can handle the new ticket types. Option B is to add more examples to the prompt by hand every time something slips. Option C is to add a second agent that double checks the first one's answers. Option D is to close the loop, capturing corrections and outcomes and feeding them back into the evals and the next update. Every end-to-end architecture runs input, processing, output, and then the part teams forget, a feedback loop that learns from what happened. The buried constraint is that nothing improves and the system drifts. So the missing piece is that feedback stage, and the answer is D. The bigger model is scale standing in for a design gap. A stronger model won't close. Adding examples by hand is a knob you keep turning forever instead of a loop that improves itself. And the second agent is over orchestration, more machinery that still never feeds a single correction back. Still solution design, now with a business goal attached. A single agent already does a research job well, but someone proposes splitting it into several specialized agents behind an orchestrator to look more scalable, and the project was funded to cut cost. Option A is to build the split because specialization always helps. Option B is to keep one agent, but on the most capable model. Option C is to split, but cache the prompts to control cost. Option D is to keep the single agent and only peel off the work that genuinely needs isolated, parallel context judged against the cost goal. The constraint is the funding reason. Cost efficiency and coordinating many agents is itself a cost you'd have to defend. The guidance is the same. Don't add agents until the problem actually requires them. So the answer is D. Splitting on principle is over orchestration. The bigger model is scale standing in for strategy. And caching a split you never needed optimizes something before you've shown it should exist. On to governance and safety. A financial assistant must never issue a payment above a set limit without human approval, and right now the only thing stopping it is a line in the system prompt. A review wants that made reliable. Option A is a stronger, more emphatic prompt. Option B is a more capable model. Option C is a hard check in code that blocks the payment and requires approval. Option D is logging every payment for later review. Here is the rule the exam leans on. When something must happen, it belongs in code, and a prompt only guides. It never guarantees. So the answer is C, enforce the limit outside the model. The stronger prompt is still guidance dressed up as a guarantee. The bigger model is scale standing in for strategy. And logging is compliance theater. It records the damage after it's already done. Still governance, now compliance. A European bank wants a customer-facing assistant, and legal asks a simple question nobody can answer yet. Where does the customer data go, and can it be deleted on request? Option A is to map the full data flow first, then apply each regulation's requirements to concrete controls. Option B is to add a privacy notice to the interface. Option C is to pick the largest model because it's the most capable. Option D is to tell the model in the prompt not to store personal data. Rules like GDPR, HIPAA, and FedRAMP are obligations on you as the deployer, and you can't meet them without knowing where the data actually flows. So the answer is A. The data flow map comes first. The privacy notice is compliance theater. The model size is irrelevant to data handling. And a prompt instruction is a guarantee the prompt can never make. Now, stakeholder communication. A client wants a contract line promising the assistant will be perfectly accurate every single time. Option A is to agree and lean on strong guardrails to hit it. Option B is to commit to a measured accuracy rate with monitoring and a clear escalation path while explaining you can't promise determinism. Option C is to promise perfection now and add logging to explain the misses later. Option D is to just restate the pitch more confidently until they sign. A probabilistic system can't be promised as if it were deterministic, so you set a service level on measured rates and you define what happens on the misses. The answer is B. Promising perfection is a guarantee the system can't keep. The logging version is compliance theater. And restating the pitch is louder, not clearer. Still stakeholders, this time about how you communicate a decision. An architect chose a cheaper, faster model for a high volume step that's slightly less accurate and now has to justify it to a business sponsor. Option A is to show both models' benchmark scores and let the sponsor pick. Option B is to walk them through the full architecture and the model internals. Option C is to keep repeating that the design is technically correct. Option D is to frame it as a decision. This option buys lower cost and latency at a small measured accuracy cost and serves the cost efficiency goal the project was funded on. The professional skill is narrating the trade-off in the language of the business goal, not the language of the model. So the answer is D. Handing over raw scores dodges the decision. The deep internals are the wrong altitude for a sponsor. And repeating that it's correct is louder, not clearer. Then developer productivity, the smallest domain on the exam. An on-call engineer is using the team's AI coding tool to diagnose a production incident, where it can read logs and propose fixes. Under time pressure, a teammate suggests giving the tool right access to production so it can apply fixes directly and close the incident faster. Option A is to keep the tool scope to read, diagnose, and propose changes and route any production change through the normal approval and deploy path. Option B is to grant the production right access, because during an incident speed matters most. Option C is to add a line to the shared instruction telling the tool to be careful with production rights. Option D is to grant the right access but log every action for review afterward. Incident speed is real, but it can't come from handing an unattended tool an irreversible power it doesn't need. So you scope it to the least privilege the job requires. So the answer is A. Keep it read and propose and send real changes through the gate that was already there. Granting broad write access is convenience over safety. A careful with production note in the instructions is a prompt pretending to be a permission. And logging every action just records the damage after it lands, which is compliance theater. This next one is multiple response. The item tells you to pick more than one, and the exam always states exactly how many, so you check each option on its own against the stem. You are hardening a production agent, and you want the changes that cut risk without adding needless complexity. Option A. Give the agent broad database write access so it never hits a permission error is false. That's convenience over safety. Option B. Remove the tools the agent's task doesn't use is true. That's least privilege. Option C. Add a supervising agent to watch the first is false. That's over orchestration. Option D. Put the one irreversible action behind a hard approval gate in code is true because a must belongs in code. So you select B and D, and the trick was never picking the ones that looked best. It was ruling each one in or out by itself. The last one, and it hides its constraint the way the real ones do. A team wants to cut the cost of a Claude feature, and halfway through the brief there's a line saying they haven't actually measured where the cost is coming from yet. Option A is to measure a baseline first, to find where the cost really lives. Option B is to turn on prompt caching right away. Option C is to switch everything to the smallest model. Option D is to add another model to verify outputs and cut rework. The buried clause is no baseline yet, and you don't optimize what you haven't measured. So the answer is A. Get the baseline first. Caching, downsizing, and an extra verifier are all reaching for a fix before anyone knows what's actually expensive. That's the whole method. One more time. The line that decided the answer was sitting in the middle of the stem waiting for you to read past it. One quiet thing before we close. When you study these, the correct letter is the least useful part. The gold is in why each wrong answer is wrong, because that's the principle you'll actually carry into a question you've never seen. So back to the question we opened with. When several answers all look right, how does an architect tell which one the exam wants? You hunt down the constraint clause, the stem buried, then you name the principle it's testing, and the winning option is almost always the one that removes something rather than adds it. Do that on every item, single answer or multiple response, and the plausible distractors stop being traps. There's one thing left that no amount of principle can fix, and that's the clock and the room on exam day. That's where we go last. How to pace the real thing and how to know you are ready.